with the lectures. So basically, I mean here, I'm putting sort of like the thing that we have been writing down on one part of the of sort of like, let's say, the whiteboard, and the other part is going to be our sort of discussions, roughly speaking. So our main objects, let me also tell you the main objects before we gonna discuss what I wrote. So the main objects for our class gonna be gonna be the Lagrangian framework. So basically, you have seen this in a standard PD class, or in a standard calculus of variations, or many kinds of physics problem boils down to minimizing some kind of Lagrangian like this. So L of gamma S, gamma dot S ds. So this is one of our main object. So it's a calculus of variation problems, right? We're gonna minimize this sort of, so we're gonna minimize this actional functional. And then we're gonna try to understand the minimizers. Gamma. So that's the first thing. We're gonna talk very deeply about that in a pretty much general setting. And then corresponding to this Lagrangian problem, it turns out that it's corresponding to the second one, is the so-called Hamiltonian ODE. Again, we're gonna see that there's a duality, there's an interplay between the Lagrangian and Hamiltonian framework, in a very beautiful way. We're gonna do from the beginning, but go very deeply, not just on the surface. So it turns out that the two problems I have written down, they look different, but they're gonna play a very sort of nicely interplay and sembro. So we will go between Hamiltonian and Lagrangian framework, and here we also try to understand the behavior of XTPT. Okay, so that's the second object that we're gonna deal with, and then the third object that come into play and sort of actually hidden behind those two problems is gonna be Hamilton-Jacobi equations. For example, I'm just gonna write down one equations. I'm gonna write down more as time goes, but this kind of problem. And finally, in terms of dynamics, the main thing that dynamical people care about are sort of like, not just existence of minimizers and Walpole's of Hamiltonian ODs. Those are easy. The key thing that people care about are sort of the long term behavior of those curves. Let's say you have gamma t as t goes to plus minus infinity, and same for xt pt as t goes to plus minus infinity. So those as very simple, right? Typically for already a very simple ODE, we care about the behaviors, whether it converges or to a sort of like to a point, or does it converge to certain sort of orbits or something like that, and various behaviors going to be of our concern. So all those, the questions look very simple, but it turns out that we're going to get really deep into them, and we're going to be able to see the interplay that really sort of like I would say that once we are done with the class, we're going to see it's really up to date how people understand about them. There are many open questions and many things that are undone compared to things that we know. Okay. So and that's the point, right? You have seen that there's a Lagrangian framework, there's a Hamiltonian framework. So there's a duality between the Lagrangian and the Hamiltonian, and that's why we need to learn about them. Okay. Here, let me come back to the lecture now. I basically just give you the motivations of why we have to study duality. In this case, the Legendre transform here. In our objects, H is the Hamiltonian. And for simplicity, I only write H depending on P now. Later on, we're going to write two variables, but because Legendre transform, we only deal with the convexity with only one variable. So H is convex, this is just a normal definition of convexity. And if in terms of this graph, it means that if you take 2 points, P and Q, then if you take the middle point P plus Q over 2, then the value of H of P plus Q over 2 is less than 1/2 of the values of HP plus HQ. And that's convexity, and convexity is essential in this whole class. Without convexity, we couldn't do much. I mean, in this framework. Okay, and we go to these simple observations. I guess that you have seen those before, but if you haven't, it's a good time to think about them. Essentially, convexity is the next simple things next to linearity. So in the discussion tab, I asked you about finding the Legendre transform of a linear function. Okay, but when you have a convex functions like this, so if HP is this convex functions, then if you try to draw all the supporting hyperplane, or all the affine function below it, and it's gonna just stay below the whole graph. And essentially you can think of the convex function as the envelopes of all the linear affine functions below. And this is a very important characterizations, that you have H of P is gonna be the supremum of all affine functions below it, and alpha in curly A can be a family, okay, depending on what. And this important characterizations actually plays lots of role in optimal control and in lots of field. Um, and this is if and only if. The proof is very simple. Um, you can prove it quickly, I would say. Okay. Right. So now let's go to Legendre transform. So I wouldn't say that Legendre transform is natural. I would honestly say that Legendre transform is not uh, transform. It's not too natural. Why do people come up with that? It's because they are looking at the supporting hyperplanes below the graph of the convex function. Um, it's not natural at all, and it's very, very, very hard to understand from the first hand. But we're gonna talk a lot about that, and I hope that after the whole class, you're gonna see that it's really beautiful. Um, and by the way, this transform is rigid. I'll tell you what do I mean by rigidity later on. So for Legendre transform, I need to assume a little bit more. I mean, just for the analysis, I tell you that it doesn't matter. That we assume that H is convex in the P variable, that's fine. And we assume more that H is superlinear. That is H of P over the length of P goes to infinity as P goes to infinity. By this, we mean that, linearity is growing like mod of P, right? So superlinearity is growing faster than mod of P, that's it. And you see that this assumption, the second assumption, is just for technical reason. Is not extremely important, but if we have that, it's better. Okay, so we define the Legendre transform. So L, so from H, I have the Legendre transform should be denoted by H star, but because of historical reason, we say that H star is L, and L, the variable is going to be V. I'll explain to you why later. So we define L of V is H star V, which is going to be the supremum of all P in Rn of P dot product with V minus H of P. So basically you just take P dot V, which is sort of like in 1D is basically a line, right? A line or a plan. And then you take that plan you take the difference between the plan and the function H of P, and you try to maximize the value. Okay. Um, so here I give you one example, and this is the example that is actually coming from classical mechanics, where there's no potential energy. So if there's no potential energy, then there's only kinetic energy. I consider H of P equal to 1/2 P square. Then in this case, you can just do computations, right? You compute L of V, which is the supremum of P in Rn of P dot with V minus 1/2 P square. What did I write here? Oh, surely I think I skipped one step here. You can just write P dot V minus 1/2 P square, and this equals to, you just complete the square, right? So you just add 1/2 V square and subtract 1/2 V square. So subtract 1/2 V square plus 1/2 P square minus P dot V. So this equals to 1/2 V square minus 1/2 of P minus V square. Okay. So if you do that, then you see that the computation equals to this value. By the way, I'm sorry that my writing is not consistent. The size sometimes is small, sometimes it's big, and I'm not good at controlling this, so sorry about this. All right. Um, so this equal to this value, and you are taking maximum value over P, right? And you're subtracting a square, right? You're subtracting a square here, and you would like to make this square equal to 0, right? So you see that LV is 1/2 of V square, and you see that the equality happens when P equals to V. All right. So we have computed the Lagrangian. Okay. And this is the actually the main example when we have the Legendre transform when Lagrange try to reformulate the classical mechanics of Newton. This is exactly the point. I'll come to this later. Then you can see that Legendre transform and Lagrangian framework gives another way to interpret Newtonian mechanics. Okay, but that's for later. Now, geometric meaning of Legendre transform. This is important. Although as I said, Legendre transform is not natural from the beginning, so it takes a while to understand it. When I first saw it, I was like, oh, this is magical, but also it was not very like intuitive. Why would we come up with that definitions? But anyway, as I said, you get used to it. Maybe some of you have seen this when you take PD1 from chapter 3 of Evans, but as I said, we're gonna go much deeper than what was written in chapter 3 of Evans. Okay. So this is a picture in 1D. You take H, which is the convex graph, and you take a plane. You are given a slope V. So P dot V is just a line of slope V, right? So you just take any line of slope V. For example, if you take this is P dot V itself, and the line can goes really down to minus infinity, and you're trying to lift it up. You're just trying to lift it up until it touches the graph H for the first time, and that's give you a supporting hyperplane, basically because it touches the graph of H, right? So for example, in the picture that I drew here, it touches the graph at this point, at this value, So when it touches the graph, I see what's my affine function then. And in that case, my affine function is P dot V plus C. Okay. So what does that mean? That means that for this particular value of C, P dot V, for this particular value of C, we have P dot V plus C minus H. the maximum value is going to be 0, right? For that value. Does that make sense? Because it's a supporting hyperplane. When it touches, the value is 0 at this point and less than 0 elsewhere. That means that the max value is equal to 0, right? And if you move C to the right, then this one gonna give you that max of P dot V minus H is gonna be minus C, okay? So basically, you know, L of V is nothing but minus of C by looking at the graph. Does that make sense? By the way, forgive me if I don't see the chat because you know it's very hard to see everything. I see your faces and I see you guys, but anyway, um, so do ask me if you have questions. Okay. Um, so that's a very cool way to think about Lagrange transform in terms of in terms of geometric meaning. Um, we get to some of this later as well. Um, so this is a first lemma based on the assumption that the Hamiltonian is convex and is superlinear. Then we have L is finite, is convex, and it's also superlinear. So we're gonna do more properties later on, but for today we're just gonna do this lemma. Okay. So let's see what good here. Actually, maybe some of you do chat, right? Give me 1 second. How do I see? Okay, right. What can we say about the geometric meaning for functions at the corner? Okay, good. We're gonna also talk about functions with corners. Okay, thanks. That's a good question because in the example we're gonna talk about one of that because when we in this picture I gave here the function looks smooth. There's no corner. There's no interesting things about that. So when the function is not smooth, then it's going to be interesting. We're going to talk about that. Okay. So let's see. All right. So the first thing is that the function is finite. Why is it finite? Okay, what I wrote down there you can see, but basically you can see it like this. P dot V has linear growth, right? For fixed V. So P dot V just have linear growth, but H of P has superlinear growth, so grow faster than linear, right? And that's why it makes the value finite. Okay. So you see that this one has superlinear growth, and this one just have linear growth. So the H of P dominates the linear growth, hence the supremum should be happening only on a ball, and hence the value is finite. Okay. All right. So that's the first thing. The second thing is that we have to show that it's convex, but convexity is simple, right? Maybe let me record here. Why is it convex? Because L of V, let me just rewrite it, supremum of all P in Rn, P dot V minus H of P. We just talked about that, right? For H of the given P, this is a linear or affine, I'm sorry. This is an affine function in V, right? So it's affine in V. And then you take supremum of a bunch of affine functions. It's exactly the earlier characterization of convex function that gives me that is convex, okay? So L is convex, right? And finally, let's show that it's superlinear. Okay, so you see that all the properties of H is being preserved to L, right? finite, convex, and superlinear. When you take the Legendre transform, you have that is finite, convex, and superlinear. So everything is preserved. Okay. So how do we show the third property? Well, um, this takes a little bit of a trick, but because you can choose P as anything you want, you know, here, right? You can choose P at anything you want. Um, so a natural way to choose P is to choose it in the same direction with V. Why? Because if you choose it in the same direction with V, then P dot V would maximize the value, right? So that's a natural choice. You can have many choices, and one choice to take P is exactly S times the unit vector in the direction of V, all right? And S to be adjusted, right? So if you take P to be like that, you plug in, you replace the supremum by one particular value. So it has to be greater than equals to, right? And you compute. The first term's gonna give you S of V. And the second terms, you take the worst case scenario, it's gonna be subtract the maximum of P less than equals to S of H of P, okay? Now, the trick now is that you fix the S, you let P goes to, sorry, you fix the S, you let V goes to infinity, right? When you divide by V and you let V goes to infinity, the S stays, right? But the second terms, when V goes to infinity, the second terms vanishes, right? So this one vanishes to zero, right? Hence, you have lim inf of LV over V is at least S, always, for any S, positive, right? That means that LV over V is going to infinity as V goes to infinity, and we are done, okay? So again, since this is a first lecture, I'm just gonna introducing to you, like this first result, um, and we're gonna go slowly as I promised, because I want to really give you all the essential and important ingredients of Hamiltonian dynamics and with KM theory. Um, um, but that's the first time. Okay. So actually now we're gonna come to exactly to one of the questions that you guys have earlier. Um, so the superlinearity of H was required so that we have L is finite, right? Because I go back here, you know, when we look at P dot V minus H of P, one has linear growth, one has superlinear growth. So the superlinearity sort of like determines that we cannot have infinity. Um, but in many examples and cases in practice, we actually don't need to assume that H is superlinear. Um, okay, so if we don't assume superlinearity, then we can still define L. However, it's clear that in such cases, L might be infinite at some places. Okay, so now let's discuss this examples. I left it for our discussions. I'm gonna do it quickly, and I'll add, address the point that you guys asked me in the chat box, and then we can do interactive discussions. So if you look at the example when we consider HP equals to P, then and what we're gonna do? Clearly, this is a cone, right? In 1D, it just a V shape, but in multi-D, it's a cone of slope 1. Clearly, it's convex. So it has linear growth. So how do you compute L of V? So first thing first, let's compute L of V. So just do computation. Uh, let's do it without using the geometric interpretation. Okay, first. So how do I compute? Let's just do L of V equal to supremum of P in Rn. P dot V minus H of P is just length of P. Okay. So already there there are things to be considered here, right? There are two cases. The first case is that, case number one is that if I have the slope of v is less than equals to 1, okay? So if slope of v is less than equals to 1, then you see that, then then uh, then p dot v minus p is always less than equals to length of p dot length of v minus length of p, right? I'm just using the whatever um, dot product inequality. There are many names for it, but I don't want to make it fancy. Okay. Uh, so it's less than equals to this, right? And because length of v is less than equals to 1, so this is less than equal to p minus p, which is 0, right? So clearly in this case, L of v is already less than equal to 0. Does that make sense? And do we have equality happens? We do, right? And equality when say when p equals to 0, right? Yeah. So that means that in first case, L of v is 0. Okay. Case number 2 is when length of v is strictly greater than 1. Okay. Again, we are just doing computation without looking into the geometric interpretation. Uh, well, you have p, you have say p dot v minus p, because length of v is greater than 1. You can make it so that p dot v is much greater than p as p goes to infinity, right? For example, you can choose it. You can choose for p chosen to be s uh, times the length of v over v, for example. Then if you chose p to be like that, the same ideas that we just did, then the first terms becomes p dot with s of, oh sorry, not p, s v over v dot with v, or maybe I'm doing it uh, no, that's true, minus the length of p, which is s, right? So this is what you have, is that you have s times the length of v minus s, and this can goes to infinity as s goes to infinity, right? So at the end of the day, what you have is that you have L of v is going to be 0 if v is less than equals to 1, and plus infinity if length of v is greater than 1. Okay. So you see, this tells us that essentially um, L might not be finite. And by the way, this is a very important example, actually. This is a solid example, very important and very useful in practice. Okay. Now let me end. I'm sorry, I'm always over time in some ways. So you look at the graph. This is h of p, right? If you look at into the graph, and if you do the geometric interpretations, if you take a plane of p dot v where mod of v is less than 1, then it's always below the graph, right? You can take many such planes, so such supporting planes. So this answers the questions of what is it has corners, and at that point you can have many supporting planes. If if length of v less than equal to 1, the supporting plane is always touching the corner at that point. Okay. And later on, you're going to see that this means that just that the subgradient of this point is just exactly the unit ball. Again, never mind, but that's what it means. Okay. And in this case, you see that h L of v is already 0, right? Because the minus c here is just 0. Okay. On the other hand, if you take p dot v if you take length of what if you take v to be greater than 1, right, then no matter what kind of graph you draw, no matter p dot v plus c you draw, it's never going to stay below your h, right? So that means that, it's going to goes to minus infinity, and it's still, going to go, higher than h at some point. What it means is that there's no supporting hyperplanes of slopes greater than 1. That means that you have plus infinity. Okay, so both of them make sense. We have both the analysis viewpoint, computations, and then the sort of geometric viewpoint that gives you sort of like the nice interplay between the two. Okay, and I think that's it for the lectures. We still have time for discussions. Why don't you discuss? I don't know how it works, but I would really like to discuss with you guys. Uh, let's see. Chat. Okay. Um, so later on, we're gonna talk about subdifferentials very soon of convex functionals. So that corresponding to the places where you have corners of a functions. That means that the function is not differentiable there. So we cannot define derivatives in general, but we can define subdifferentials. Um, if you have done research or courses on convex analysis or something related, this is a very natural object. But if you haven't done that, it's fine. We're gonna start from the beginning. So I mean, I wouldn't be worried about that. Okay. Any concerns, questions? Uh,
Um,
yes.
excuse me. So if the
Mm-hmm.
function is still superlinear but
Mm-hmm.
have many corners,
Mm-hmm.
then we are basically finding the largest loop, or the largest loop that it could still be.
Mm-hmm. Mm-hmm.
I mean, under the curve, right? So in
Yes.
that case, okay.
Yes. Okay. Yeah, so that's good actually. So maybe let's see. By the way, can you see me writing clearly? Okay. Yeah, thanks. I have been trying to think a lot because I was trying to write in a sort of like paper size, but then when I do the lectures, I want to rotate it so that I have sort of space to anyway. It's hard this time, but on the other hand, I told my students and myself and my family that even when we come back to normal, there are things that are going to change forever. And it might be good to keep in our minds that if we have good ideas, we can carry them with us, to the later time. And that might be really helpful for ourselves and for our friends and peers and others, So that's my way to like that. So that's a very good questions in the same line with the example. So let's try to design a function like this. So another example. So you have this kind of functions. Okay, pardon my drawing. Maybe I'm trying to make it sharper. Oh, the more I draw, the more crazy I make. Anyway, so there are corners here. So this is the example of H, right? So in this example, you can see that um, that clearly is still super linear growth, but there are corners. So if you do, there are three corners. So if you do the the geometric meanings at this first corner, if you draw graphs like that, and you see that at that point the value is 0, right? So you can see that at least geometrically I should have L of V should be something like 0 for V less than equal to some slopes, whatever that is, maybe 1/2. I don't know, I'm just making it up. So slope 1/2. Okay, this line has slope 1/2. Okay, And then if you take further slopes, if you take other slopes, and once you pass one half, you can if you pass one half, then this is going to be the next point of touching, that you can draw graphs like, okay, you can draw graph like, hold on. Give me 1 second. I'm not good at drawing here, and I don't want to uh, maybe let me change this one so that it's easier to draw a picture. So if I change the graph so that it has few corners like this, okay, so it's easier for me to draw a picture. Then the next point that is interesting for you is this corner, right? Because it's still having the other corner. And then you're gonna start drawing graphs like this one. It's going down like that, and then the thing in the between is gonna go like that. Okay. So you see that in the next slopes, that you can touch the graph, right? Maybe okay. Maybe this one I'm gonna say that is slope 1. So between slope 1/2 and slope 1, you're sort of like turning the sort of like the affine functions, right? And it touching the graph at exactly this point. And for each of the point, you can see that you're exactly drawing this supporting hyperplane. Okay. And you can do computation to see what's the value. Does that make sense? Yeah. So that's beautiful. And what it means is that at the corners you have more supporting hyperplanes than usual, right? Because in terms of geometric interpretations of derivatives, if you can touch it by exactly one plane, then the function is differentiable there. Does that make sense? When it has a corner, it's not differentiable, then you can touch it with more supporting hyperplanes. Okay. Yeah. But don't worry, I mean, we're gonna talk about this, but most of the times when we talk about Hamiltonians and Lagrangians mechanics, then we're gonna talk about smooth enough functions. There's certain interplays. Okay. Other concerns?
So are you expecting us to already have some PDE background in this class?
No. No, that's also a good question. It's a plus if you have that, but you see that I'm redoing everything from the beginning. Um, we start from Lojang transform and we are constructing things, and I'm going to talk about minimizing problems. For example, I'm going to talk about the problem with minimizing the Lagrangian here, this problem. And I will prove from the beginning that we have a minimizers, we have a regularity of a minimizers, and we prove everything. I would say that it's a plus if you know some PDs like PD1, but it wouldn't be a problem. Does that answer your question?
Yeah, thank you.
Okay. Yeah, but and also I strongly suggest that you guys do discussions, with your peer. Um, So next time, surely we're gonna talk more, and you see that I'll try to post my second lecture by tonight. Um, so we have shown that L equal to H star, uh, that it keeps all the properties of H, right? So next time we're gonna show that L star, which is H double star. So if we take the Lagrange transform once more of L, we get back to H. And this is beautiful. This is mysterious. I mean, uh, again, we can prove it, and honestly, it was not clear at all to me uh, why it would be true, right? I mean, okay, we can do analysis, we can do things, but understanding it deep, as deep as we can is another thing. And actually, it turns out that only 10 years ago, there was a paper in the Annals by, I forgot the names of the authors, I'm sorry. But I put it in the appendix of my book that they proved only 10 years ago that all the transformations have this kind of properties have to be essentially Legendre transforms. It's amazing. Only 10 years ago. So you can read the appendix of my book for fun. I put it there just because it's beautiful. Sometimes
Sorry.
it's just, yeah.
Oh, excuse me. Does that imply that Fourier transform is basically Lagrange transform?
Okay, I wouldn't go that far. No, you are right. I mean, I am being vague here, right? Because Fourier transform, you do it twice, it's also coming back. So Legendre transform is kind of a nonlinear thing, and you have to read the theorem, right? Because there are assumptions that I put there. So I'm saying it here without any assumptions, and without any assumption, anything can be true.
Yep.
You can just define or transform, right? I transform H to be something, and then I transform it once, it becomes H. So.
Yeah.
But what I mean is that it's beautiful, and that's a great proof. I just put it there for fun. I have never used it, and I don't think that it's gonna be used for our purposes. But what I mean is it's mysterious, and it's normal if we feel that it's kind of like weird. Um, but you will see that from the mechanic viewpoint, people define Legendre transform because it's natural from mechanics viewpoint. It's gonna take us some more lectures to go there, but okay. Is it clear? Good. Right. Yeah, I think that's it for today. I'll post the after class slides on the course web page as well, and then the video should appear on the course web page as well. But I was told that we only have 10 gigabytes of memory, so I might run into trouble very soon. I might need to upload our videos to YouTube, but because we have all of us here, I wouldn't let the public watch it. So I need to find a way to handle this. Anyhow, okay, I see. I think there's one more question or something.
I'm just saying you could use Google Drive instead. You have unlimited storage on Google Drive through the university, and you can also integrate it with Canvas. So
Okay.
It's an option.
Okay, thanks.
And we would all just like be members of a drive or something. Sorry.
Okay, thanks. I'll figure it out this week. I mean, I have been sort of thinking about what's the best idea to store the videos for all of you and for me as well. I for later on, maybe some of my students, 10 years later want to study weekend was like, okay, watch the videos, Anyhow, okay. So I'll see you on Wednesday. See you. Bye-bye. And
Bye.
okay, thank you.
Thank you.
Bye-bye.